Good morning everyone. I'll be presenting my paper, The Mixed-Use Matrix, Developing Design Guidelines for the Mixed-Use Typology for Bombay. So, why mixed-use typologies? Mixed-use typologies have been of interest in many research already due to their conducive sustainable framework. As they're a keen mixture of various programs, this automatically reduces emissions, encourages walkability, health, and thereby is the best suited typology into promoting what's often referred to as the triple bottom line, that's people, profit, and planet. Why is this of interest in Bombay's context? Mumbai is constantly growing its building stock, but facing a land scarcity. Within that fabric, mixed-use typologies show great promise and have yet to be explored for this city. Therefore, this paper focuses on coming up with guidelines that would aid planners in the early stages of mixed-use design. How is this being done? So the method starts with establishing a base case or a precedent. Through this precedent, sensitivity studies were conducted both at micro and macro level. One, to understand the impact of large-scale mixed-use developments on urban heat island. The massing study is then furthered into building level studies with a correlation between massing, cooling load, and daylight is arrived upon. Using these studies, a guideline or framework to aid designers with the master planning decisions are created. So as a base case, the only proposed mixed-use development in the city was used for this paper. This is Kohinoor Square, an under construction mixed-use development in the heart of Bombay's central district of Dadar. The percentage of programmatic breakdown was maintained through the rest of the studies. The first set of studies were conducted on a master planning level or a massing level to assess a built form's impact on urban heat island. The Ladybug family tool Dragonfly was used. This enables us to generate a modified weather data specific to the geometric configuration of the given site. So this graph shows the difference between the dry bulb temperature of the city extracted through the APW and the dry bulb of the site. The metric will be referred to as delta T and carried out as a metric for further testing. Sensitivity tests were carried out for parameters such as ground cover percentage of green cover on site to establish the more crucial parameter with respect to urban heat island. While it's observable that ground cover had a direct correlation with delta T, not much of an effect was generated with green cover. And upon further study, it was noticeable that this was due to a limitation in the tool's ability to carry out complex soil computation. Therefore, the impact of ground cover, that is density, was chosen to study further. Using Grasshopper's native solver, numerous options for massing strategies with the solver set to lowering incident radiation were created. Through these studies, it could be seen that density and urban heat island effect have a negative correlation. That is, more sprawl the development, lower its urban heat island potential. This, however, is in stark contrast to prevalent literature that promotes denser solutions for lowering cooling loads in tropical countries. Therefore, in the next set of studies, 20 of the most representative massing solutions, that is containing median, maximum and minimum best and worst case solutions, were computed for both cooling load and daylight levels. The metric chosen was DLA, with each massing iteration using the modified weather file generated using Dragonfly, and then the cooling load was generated. A regression curve was plotted for cooling load against the average surface to volume ratio. This showed a strong correlation suggesting that higher the surface to volume ratio, higher the cooling load. The same iterations were also studied for average daylight levels. The metric used here was daylight autonomy for 300 lux. Here it's observed that while the surface to volume ratios changed, the daylight levels remain fairly constant. It's important to note here that the glazing properties and the WWR were kept constant through all iterations, thereby suggesting that those two parameters are more imperative to daylight than surface to volume. And so the more critical feature in massing is thermal performance. It's important to note that in both cases, defaults and other values considered for schedules, construction sets, etc. are detailed in the paper, and for the ease of current understanding, it can be mentioned that ASHE defaults were used for both base case, macro and microclimate level studies to maintain uniformity. So inferences were culled out through both studies, and they are as follows. So it was observed that massing that creates more overlaps and overshading reduces incident radiation, thereby reducing the urban heat island effect. Overlapping forms of medium density showed better results in outdoor studies. Low density sprawls also perform better than high-rise massing in terms of heat island. However, these massing schemes had a very high cooling load due to increased surface volume exposure. Intersecting geometry with medium to high surface to volume also produced median cooling loads. This can be attributed to the self-shading of forms. High rises, which in turn have more surface to volume, also do not benefit in urban heat island, and neither do they benefit in reducing cooling loads. So a medium density with longer facades flanking internal courts had lower cooling loads compared to the more exposed mid-rise schemes, despite their surface to volume ratio being more median value than the lower half. So using those inferences, a set of guidelines or the matrix was started to be developed. The massing is primarily divided into density-based typologies, that's high, mid and low rise. Each of those types are further divided into podium types or courtyard enclosing. Each massing strategy is evaluated for its performance against urban heat island effect and cooling load as suggested by the previous studies. They are graded by least to most important by growing sizes of circles, indicative of the measure of impact. The circles are also color coded for in, out and overall. For each strategy, a set of design features that can be adopted for improving the performance of that strategy is also provided. These include shading, form alteration, from orientation or twisting, an increase in green cover through landscape or green roof. The features are limited to these, as these are the ones that have a direct impact only in the early design stages. So to conclude, as mentioned in the introduction, this paper hopes to provide a kickstart to design explorative ventures towards mixed-use developments in Bombay. As the studies suggest, a variety of massing approaches can be utilized to ensure performance with atmosphere while catering to density requirements of the city. If considered early on, design decisions for catalytic developments such as mixed-use developments can promote sustainable growth across the entire urban fabric. In a direction forward, the research will continue to incorporate effects of wind from an outdoor and indoor ventilation perspective. High-level energy performance numbers could also generate speculative renewable energy potential. And lastly, provide base insight into embodied carbon or life cycle benefits from pursuing mixed-use goals. Thank you so much.